welcome back to my channel. Today we are going to be considering this question of a simply supported beam at both ends with a pin joint at one end and a roller support at the other end, and the point load F is being applied at the midspan, and so we have to use energy methods, more specifically conservation of energy, to show that the deflection at the midspan, the maximum deflection, is given by this expression, where this is the force, that's the length of the beam, and this is the Young's modulus and the second moment of area about the z-axis. So Vmax will obviously be at the midspan. Okay, so conservation of energy says that the internal strain energy experienced by the material, or this beam, is equal to the external work done on the beam. Where the external work is easy, it's just given by a half deflection, and this is assuming a quasi-static loading, where the graph exhibited by force over time would be linear with compared to a dynamic loading, which is not what we're considering here. The force over time would be a constant force because suddenly at t equals 0 you suddenly have the force, but for here at t equals 0 you have 0 force and then it gradually increases. So this quasi means it's occurring slowly. And the strain energy is given by a half integral of L to 0 of the bending moment as a function of x. So I'll call it mz as a function of x squared all over this product of ei, which is a constant, so we can take it out of the integral, and this is with respect to x. So taking it out of the integral, we get 1 over 2 ei integral L to 0 of mz function of x squared dx. Okay, so the first thing we have to do is draw a free body diagram and identify the forces acting on the beam. So we have the beam here. So this is a roller support on the right, so we only have a vertical force. Call it this B, this is point A. So this will be R, B, Y because it's vertical. And for the pin joint we have both horizontal and vertical, so RAY and RAX. But since we have no other horizontal forces, this will just be equal to 0. And we have a force in the middle. So from symmetry, since this is L over 2 and this is L over 2, the reaction A will be equal to the reaction BY. They will be the same and they will equal half the force since it's acting at the midspan. This is only applicable at a special scenario where you have symmetry down the middle. Okay, so now we have obtained expression for the reaction forces. We can now take a cut at the beam, say somewhere before the force, say here, and we take moments about the cut. So let's say we cut it here, draw it down here somewhere. Still have the force F acting. We have this reaction force here. This is the pin joint. So taking moments about here, about the cut, we will get So mz acts here, and we have an internal shear force, but we are going to ignore that for now, as we are not we're not interested in this. We're interested in finding the bending moment in the integral. So taking moments, we have it's acting clockwise, and the force F will be going in the same direction. And that is, so the distance to the cut is x, the distance to the F force is L/2 from the end to the force, and so to get to the cut we do L/2 minus x. And for the RBY force, this is acting against the moment, so we have a negative RBY times L minus x. And forgot to add the moment, and this is all equal to 0. So rearranging for mz, we get RBY L minus x minus F L/2 minus x. Okay, now we have an expression for mz. We can put this in the integral and then integrate. So we have u equals 1/2 ei integral L to 0 of RBY, which we said was f/2, so we can just plug that straight in. f/2 L minus x. We can remove the Macaulay bracket now because we are integrating, so we can just treat it as a normal bracket. Minus f L/2 minus x. If we simplify this expression here, to make our lives easier, so take out the 2 on this side, so we get f/2 L minus x minus f/2 L minus x/2, and then factor, so we get f/2 L minus x minus L plus x/2, distributing this minus to these two. So L minus L is 0, minus x plus x/2 is minus x/2. Take out the minus and rewrite, so we get mz of x, so going to the next page, we have just f/2 minus, and this is going to be x times x/2. So this is just the same as the minus fx/4. Okay, so going back to the integral, we have u equals 1/2 ei integral L to 0 of minus fx/4 dx. Okay. Sorry, this is squared because it's mz squared. So integrating this, well, f/4 is just a constant. We can take that out of the integral. F squared over 4 squared is 16 times 2 is 32. 32 ei integral L to 0 of x squared dx. You can just plug this straight into your calculator. Actually, we don't know L, so if we knew L, we could just find that easily, but let's just integrate. So f squared over 32 ei integral of this is going to be that, x cubed over 3. Plugging in L, we get L cubed over 3 and then times it long, because the 0 just makes it vanish. So f squared L cubed over 32 ei. Okay. sorry, I forgot to times by 3, so this is going to be 96. So that's your strain energy, equating that to the work done, which we defined over here. So we get F squared L cubed over 96 EI equals to 1/2 F bending, deflection due to bending. So rearranging for the deflection, we get FL cubed over 48 EI, which is exactly what they wanted us to find.